Hi there. What you're seeing here is an energy-based model that learns the concept of a shape from a demonstration on the left. So on the left, you can see a demonstration of data points sampled from a shape, in these cases, circles or squares, and then the corresponding energy function that the model infers from that. And then it can replicate that shape on the right using that energy function. So the paper we're going to analyze today is called Concept Learning with Energy-Based Models by Igor Mordac of OpenAI. And this is a very cool paper, or at least I think it's a very cool paper. But it is also a very hard paper. So therefore, first I want to kind of make a bit of an introduction into the concepts that we are facing in this paper. So the first thing you need to know are energy functions or energy-based models. What is an energy function? An energy function, sometimes called E, is simply a function with one or multiple inputs. Let's call them X. And you can make if the energy function is happy with X, it will be the value 0. And if the energy function is not happy with X, it will be a high value, like larger than 0. So this is happy, this is not happy. So let's give some examples of this. We can formulate almost any machine learning problem in terms of an energy function. Let's say we have a classifier. The classifier is takes as an input an image here, maybe of a cat, and a label. So if the label is cat, then the energy will be 0 if the energy function is, of course, working correctly. And if we give the energy function the same image, but we give it a wrong label, dog, then it is very high. In the case of the classifier, of course, we can simply take the loss function as the energy function, and we automatically get an energy-based model. So the loss function here would be something like the negative log probability of the correct class. But in any case, it is just going to be a high number. Let's call it 10 to the 9. So the energy function says, this is very bad. This thing here is very bad. The entire thing you input. It won't tell you yet what's bad about it. So that also means you can change any of the two things to make the classifier happy. Now, usually we're concerned with changing the label, right? It's like, tell me which other label do I need to input to make you happy? And if we make the labels differentiable, of course, we never input the true label. We actually input like a distribution, a softmax distribution over labels, and that's differentiable. We can use gradient descent to update the dog label. We can use gradient descent to find a label that would make the energy function more happy. So we could use gradient descent to get the cat level if we had a good classifier. But we can also optimize the image to make it compatible with the dog label, right? That's things that, if you ever saw Deep Dream or something like this, those models do exactly that. They optimize the input image for a particular label. And there you can view the entire neural network, including the loss function, as the energy function. So what's another example? Another example is, let's say you have a k-means model, and the energy function is simply we input a data point. And for the data point, what you're going to do is you're going to find the min cluster index, the min k, over, you have your multiple clusters here, and your data point might be here. So you're going to find the cluster that's closest, and then the distance here, this distance d, will be the energy of that. So the model is very happy when your data point comes from one of the clusters, but your model is not happy when the data point is far away. And that would be the cost function of the k-means function. So that's an energy-based model too. Now, currently, energy-based models have come into fashion through things like GANs or any sort of noise contrastive estimation. So in a GAN, what you have is you have a discriminator. And the discriminator will basically learn a function to differentiate data from non-data. So that by itself is an energy function. So the discriminator will learn a function, and that function will be low wherever the discriminator thinks there is data, right? So it will usually do this around the data points. So the data points form the valleys right here. And then the generator will basically take that discriminator function and will try to infer points that are also in these valleys, to produce points that are also in the valleys. And then you basically have an energy learning competition. The discriminator now tries to push down on the energy where the true data is and push up on the energy where the generated data is. And that will give you basically a steeper energy-based function in the future. I hope. So in this case, the discriminator neural network is the energy function. And the generator just tries to produce data that is compatible with that energy function. So I hope that concept of what an energy function is a bit clear. Any machine learning problem can be formulated in terms of an energy function. Now, what is not done so far is what we alluded to a little bit before in the classifier example, and also here. So right now, when we want to train again, we simply take the generator to produce data. Now, what's the generator's goal? The generator's goal is to hit those valleys in the energy function, right? And we produce a generator in one shot produce this data. But what we could also do is, of course, we could just start somewhere. Let's say here, we pick a random data point, and then we use gradient descent because the energy function in this case is smooth. We use gradient descent to just drop down this valley and then find ourselves in this valley. So without ever training a generator, we can use these methods to produce points that are in the valley of the energy function, right? And this, I don't know if people, I guess people have trained GANs like this. The reason why it doesn't work, let's say in the real world, is because that procedure will just produce adversarial examples for the discriminator. And those usually look like nothing like data, because if you keep the discriminator just stable and gradient descent against it, what you'll get isn't really qualitatively good. But in principle, if the discriminator was a good energy function for the data to describe the data, we could use gradient descent. The same up here. In order to find a good label for an image, given that we have a good energy function, right? So this is that. We could simply gradient descent on the label in order to find a better label. So in this paper, we're going to have a situation where we say we're given an energy function and we're given a bunch of inputs. They are then called X, A, and W. And if I have my energy function already, if I have given my energy function, and I have given two of those three things, any two, right, I can infer the last thing simply by gradient descent on my energy function, because I know the energy function is 0 when when the energy function is happy with the input. So when all of these things agree, basically the energy function is happy, it will output 0, otherwise it will output a high value. Therefore, if I'm given any two of those three things, I can find a compatible third thing by descending. And then, of course, over here in these machine learning problems, the task was always actually to learn an energy function, right? So usually in the training data set, we are given images and labels, and we want to learn this energy function, which would be parameterized. So we want to learn the parameters. And the same here in our general case, if we are now given three things, but we are not given the parameters of the energy function, we don't know what those are. As long as we're given all of the inputs in our training data set, and our training data set guarantees these are actually, these are inputs that are compatible with each other, the energy function should be low, we can simply gradient descent on the parameters of the energy function. So in a sense, there are four things, right? There are these three inputs, and then there are the parameters of the energy function. If we're given any three of those four, we can gradient descent on the rest. And that's going to be the basis. So the x here is going to be the so-called state. And the state in this paper is going to be images of entities. The entities, sorry, it's not going to be images, but the entities are these little circles that you're going to see. And each of those entities can have an X position, a Y position, and I believe a color, so R, G, and B. So each of those can have that. And then the concatenation of all of those attributes is one big vector, and that is your X, that's your state. So state is number of entities and their attributes. A is going to be an attention mask over the state. So A is going to be, here you have four entities. So A will have four entries telling you which of these entities you should pay attention to right now. And W is going to be a concept vector, so-called. So W is going to be the embedding of a concept. Now, what a concept is in this case is very general. I can give you an example. One concept is, do the entities that the A pays attention to, are they close to each other? So in this case, you see we have two entities that A has a high value on, and this is this ball up here and this ball down here. Now, if the concept vector is the embedding for the concept of being close to each other, then the energy function would be very happy if those two things are close to each other, and it would be very unhappy if those two things aren't close to each other. But in the very same situation, so the same X, the same attention mask, but a different concept, so a different W vector right here, then the energy function would be maybe very happy if the two things are far apart, and maybe unhappy if the two things are close. So the question is always, how are the three things that you put into the energy function compatible with each other? And given all but one of these things, you can infer the other. So let's say you have a perfect energy function for this situation. Right? You're just given the energy function. You can trust it. And you are given, let's make an example. You are given the X, so you're given the state. I'm going to draw the state down here. Right? Okay. This is the state. And you are given the W, and the W is the embedding. It's a vector, but in embedding space. But the embedding is for a line. Right? So the geometric unit of a line. Now your task is to find A, the attention mask that will make the energy function happy. And as you can see right here, what you would do is you would put a lot of weight on this, and this ball, and no weight on that ball, because those make a line. And since everything here is differentiable, so the state is differentiable, the attention is differentiable, and the concept or vectors, they're differentiable, you can use gradient descent to find that. Another example, if you're given, again, the same W, so line, and you are given this following thing, and you're given the attention on these three, and you say, please find the X, please find the X, the state that makes this energy function happy. Now this here you would call the starting state, the X0. Your task is going to be find the X1. Find the state. How do you have to change this state such that the energy function is happy? And of course, the answer is going to be is to push this ball here inward until it is in the middle of the two others, so the three form a line. Right, these three form a line. You don't have to do anything to this ball up here because there is no attention on it. And the attention, it's only is the concept for the things that you put attention on and the state, are those three in agreement, then the energy function is happy. Okay, we have covered the basics. Now let's dive into the paper. I think this is the longest introduction ever, but I think it will pay off once you see. So they specifically, or this author, I think it's a single author, identifies two different things that you can do with an energy function here. Of course, you can do more, as we saw, but they identified two. So here is where you have given the initial state and an attention mask, and you want to find the x1, the state that satisfies the concept and attention the most. This the author calls generation. As you can see here, these four things that you have the attention on are pushed around until they make a square, because the concept right now is square. And in the other case, where you are given this x0 and x1, just call this x right here. Just call this thing x. If you're given those two and you are given the concept square and you're tasked with finding A, the attention mask, of course, you're going to put the attention on these right here. And that is going to happen through gradient descent. Again, we're not learning a model to give you that attention. Like in a GAN, we're learning a generator to just one shot give it to you. Right now, what we're going to do is we're going to gradient descent optimize on our smooth energy function to give us that perfect attention mask that satisfies the energy function. All right, so this is the difference right here. Gradient descent is part of the output procedure of the model. Usually we just use it to learn, and we learn a one-shot model, but here gradient descent is part of the model. So they introduce energy functions here, and they say, okay, we can have a policy on X. So if we're given a concept W, and if we're given an A, we can have a policy over X, which basically means we can find X's that are compatible with that by running gradient descent here. You see there is an xk minus 1, and we are running gradient descent on the energy function with respect to X to find a better X that satisfies the energy function given those inputs. And the same if we want to find an attention mask, we are running gradient descent on the attention mask, again, in order to satisfy the same energy function. So you see the inputs are both times the same. The concept here we can input square, here we can input square, but the difference is what we're running gradient descent on and what we keep constant. And I would add a third line here actually, because we can also, if we're given an X and an A, we can also infer a W, and that's going to be an integral part. So if I have this right here and this situation, and I have, say, I have attention on these four, now I can ask the model, so I am given X and I'm given A, I can ask the model to infer W. And the model should ideally output, this is square. Now the model isn't going to output square, the model is going to output a vector representation of square, right? So the model is going to output square, but as a vector of numbers, because that's how we've trained it. W is an embedding. But what we can then do later is we can say, okay, I'm not going to tell you it's a square, you just come up with a vector W that describes this situation, right? And now I'm going to take that vector W that you came up with, Mr. or Mrs. Model, and I'm going to tell you a new situation. This situation right here. And I'm going to now give you X, and I'm going to give you the W that you yourself have output, and now please tell me what's the A. And then the model is, of course, supposed to tell you, oh, these 4 here are the A. So without ever telling that it should be a square, what you can do is you can let the model infer a W from one example situation and then transfer that W to a new situation. Right? So it can identify, you can just say, whatever concept I have up here, please apply that same concept, which is the W, down here. And this is the entire paper now. This is the concept learning through energy-based models. Okay, so that is kind of a third line I would add down here. You can infer a concept vector if you're given the X and the A. So in order to do all this, their energy function is going to be a so-called relational neural network. So what you'll have is you'll have a simple neural network, a multi-layer perceptron that always connects 2 entities to each other with the concept vector. And then this is, I believe, a sigmoid that connects the attention masks of the 2. And then you simply sum over all pairs of 2 entries in your model, and then you send that through an MLP again. This, I believe, is not so important. It's just important that they can feed this entire situation, the X, the A, and the W. They can basically feed into a neural network, and the neural network comes up with a number of how well those 3 things fit together. And then you can transfer these concepts. That's pretty cool. Now, the only question is, of course, we've always said, we're given an energy function. We just have it. But of course, this is a neural network, and the neural network has parameters. And the parameters, we don't know what good parameters are at the beginning. So we need to train this thing. And again, the reason why these are toy problems right here is, I mean, we'll get to why it's computational, but this is kind of a new field, I believe, in machine learning. At least I come from classical machine learning, and we only ever have used like SGD to train, and we only ever have produced models that one shot produce something. And here, I believe this is a new concept where you use gradient descent as part of the output. And that makes a lot of trouble, so that's why we work in toy problems. So this here is the situation I described. You have a demo event where you're given the X and the A, and you're supposed to infer the W. So the question here is, what's the W? And the model will come up with a W, and you're not going to do anything right now. You're simply going to take that W and tell it, oh, well, here is a so-called test event. So please apply the W you came up with in this test event. And please find me the A, in this case, that satisfies the W and the X I give you here. And of course, the A right here is, as you can see, even you don't know that it's a square. And the actual concept here is move the gray ball to the middle of the square, right? That is it here. But no one has told me this. I just looked at the picture. So the correct answer here would be to place attention on those 4 things, and then to take this thing and move it to the middle right here in this over here. So that would be the correct answer. Now the question is, how do you train something like this? And they show that so this is the loss function right here. The loss function is they give you a concept and an initial situation, and you're supposed to infer the X1 and the A, and the loss function is simply the negative log likelihood of that. But what does that mean? So we'll make it easier. If you have this procedure right here, right, where you have a demo event, this up here, this is demo, and this is a test event. How are you going, this entire procedure, how are you going to learn the energy function? Well, in this case, this entire procedure, this entire thing is one training sample. sample. But usually we have input and label. And now here it's much more complicated because, so we have input, okay, that's this X and this A, cool. But then we have SGD as integral part of the procedure to determine the W. And now what we could do is just apply a loss to the W, but we don't, because we don't know what the embedding space for the concepts is. We could maybe train a classifier, but in this case, we want to train the ability to transfer these concepts. So our training sample needs to be one time transferring a concept. So SGD for one is part of our process here. And not only that, but then this X here, of course, is also part of our training sample, right? This up here is X0 and this here is X1. And now we need to find this A, this attention mask. And that is an SGD again. Remember, inferring anything through the energy function is a gradient descent process. So ultimately, our one training example consists of X0, A at the beginning, so let's call that A0. It consists of the SGD procedure to find W. It consists of X1, and it consists of the SGD procedure to find A, the A1, the output A. And then that will give us the output A, the A1. So this here is our input in the classical machine learning. This would be our X, and this here would be our label Y. And that's what we train on. We train so such that the output right here, the A, this is of course the Y hat. This is what we predict. And in the training sample, we just write a little generator that will, make this situation that knows what the concept is, right? It will say, okay, I'm going to make an example for a square. Then it will make this, will make the attention mask for a square. And then it will make the new situation again with a square, but not tell us the attention mask there. And it will make the attention mask into the true Y. So at the end, we can compare what our model output, the attention mask we output here, without ever knowing that this should be a square, right? And we have the true label, which comes out of the generator that at the beginning decided that it should be a square. And then the loss, the distance between those two, that's our loss. This is an enormous procedure to get a loss. And most crucially, you have to backpropagate through optimization procedures. And this is something that we just can't do yet in our models. If you take an image at ResNet 50, right now we do one forward propagation to get a label. In this procedure, if you had to backpropagate through the optimization procedure, for each sample, you would need to basically backpropagate through 50 forward passes of the ResNet if your optimization procedure is 50 steps long. And that is just not feasible right now. So that's why we don't do it. But I believe maybe once we find a smart way of backpropping through optimization procedures, a whole lot of these things will become a new wave in machine learning. I'm excited by this. I'm pretty sure it doesn't work yet, and this is very fiddly work, but I'm excited by the prospect that we can do this. So this is the training procedure, right? You are given X0, X1, and A, and you optimize in order to infer the concept behind it, right? The generator, your level generator of your training data, it knows the concept. It has a concept in mind when it generated this, but you're not telling your model what the concept is. It needs to infer that. And then using the thing that the model inferred, you can either give it X0 and X1 and infer A, or you can give it the X and the A and infer X. You can do either of those, right? These are called identification or generation respectively. And then you compare the output here to what the generator at the beginning thought. Again, it's not telling you. That's because that's the label. And you compare this to that, and that will be your loss to train your energy function parameters. So your training samples, if you think of this entire thing as one forward pass of the model, then it's just classic machine learning, right? You have a training sample, which is one forward pass, and you have a corresponding label that you infer. So let's jump to the experiments right here. The experiments are actually pretty cool. So what they've done is, for example, taken the concept of being far apart from something. Now, being far apart, so that the little x needs to be as far away as possible from the ball that has the attention on it, right? So if you do generation and you start the little x right here and you ask the model, please infer the next state of the world, it will push that little x away right here. And in color, you can see the energy function values of the position of the x. So it pushes it away from this thing. But if you take the same concept embedding, the concept embedding of being far away, but you don't do generation, you do identification, which means you infer the A, then it will simply tell you that this ball right here is the furthest away from the X, right? So you can do all sorts of things like this and transferring concepts. I find this here pretty interesting. So they have two different concepts. One concept is red as an identification. You need to identify the red ball. But the other concept is you need to turn something red, right? You need to take a ball that is maybe now blue, and of course the color, you can gradient descent on the colors. You need to make it red. And since the energy function, it just takes three input, X, A, and W. It doesn't, you're not going to tell it right now in which situation you are. It has to create this W embedding space through learning. And if you do it with those two concepts, then it will put the make something red concept and the is something red concepts in the same places. So this is a PCA, and in blue, I think blue is the attention codes for identify the red things, and in red are the generation code for make something red, and they will be put in the same place, which is pretty cool. It means that the energy function really learns the feature of something being red. I find this pretty neat. And then here they have some experiments where they basically show we need that gradient descent optimization procedure because only after many steps will the energy function basically be aligned with the concept that you want. So if you have a zero-shot model, like just one forward pass, as we do here, you'll see that the energy function that is supposed to make a circle from samples, right? This is the example concept right here. If you just have a one-shot model, it cannot, or in this case at least, it doesn't learn to one-shot produce. Only if you optimize for a few steps will it get this. So you optimize at inference time, and that seems to be very important. You can see again here demonstrations of this. So the example is this, and then the model, as you can see, after 20 steps, optimizes the points to go to these locations. Whereas after only one step, it didn't do that yet. So there are complex things at work here. And this column here is where you don't have a relational neural network. So you can't basically capture dependencies between things. So you have no chance of making a square because you don't know where the things are in relation to each other. But that's more of an engineering question. Their point is basically that if you have models that do optimization at inference time, they are much more powerful than models that just do a one-shot forward pass. It's sort of like an autoregressive model in NLP versus a non-autoregressive model that produces all words at once. If you produce all words of a sentence at once, no word can depend on any other word, and you can just produce independent, or you produce independent things, which will make the sentence often not make any sense. Right? they also have this KL objective, which is a regularizer, which I believe that's just a trial and error. They built it in because, but it is a regularizer. I don't want to really go into that. And then they do a demonstration and they reenact it on a robot. The demonstration here is that there is a situation where two things have a tension on, and you're supposed to move something into the middle of the two things. So that's the you don't tell the robot the concept. It needs to learn that from data and then infer that this is the concept that you want, and then transfer that to the other environment. Now, there's this robot environment, but ultimately they still encode the positions of these things and the position of that. And really all you have to do different here is that instead of moving this actuator directly, you need to calculate what you need to do to the individual joints in the robot. So I think this is maybe because it's OpenAI and it needs to, look robot-y and stuff, but the problem here is not really different. It's not real world transfer or anything. So yeah, let's go through some of the things they can learn with this. So you can see here, they can learn these regional geometric shapes. And so on the left is the example event that the model needs to take the concept from. Now this is, I believe, very much identification. So what they did is they trained with a data set where all of these appear, right? So there are squares, there are lines, there are circles. So this is maybe my criticism here, that it is not so much to generally infer a concept. It is more like identify the concept. So the model basically just needs to decide, is this line, is this circle, or is this square? Because those things were in the training data set. It would be nice to see how this generalizes to general concepts, or if we can even make that, if we can have a zero-shot concept inference and then transfer those concepts to other things. Maybe that's already happening. I don't know. So here, the spatial arrangement is to either be close to something or to be between two things. So if the attention is on two things, you want in between. So you see the top ones are the demonstrations. It needs to recognize the concept and it needs to basically optimize to fulfill that concept. Shapes, so to make shapes is, oh yeah, there's a triangle, right? Again, this very much, I believe, relies on recognition and not actual understanding of what a triangle is. Here you have proximity, being close or being far apart. What else is cool? Oh yeah, you have the recognition for the same task, right? You need to identify the ball that is close or far. And here you really also see the optimization procedure in action, where, for example, at the beginning of each flicker, you kind of see the attention being everywhere and then stabilizing to 1 or 2 points. So if 2 points are equally close or far apart, you'll see the attention being on multiple points, which is pretty cool, right? So that means the model really learns this concept. Here's the count quantity. So you can either have 1, 2, or larger than 3 or something. Yeah, that seems like they tried 3 and 4 and didn't work, so they just said, oh, we'll just do larger than 3. And here's this robot thing where it also always needs to move in between. Now this is the part that I'm not really impressed with, but whatever. Whatever you want. Okay, I hope this was a good introduction to energy functions, what you can do with them, what I think of them, and of this paper. It is a pretty cool paper. Yes, it only works on toy problems so far, but I believe this is one interesting direction of future machine learning, and something yet to be very much explored. If you like this content, please subscribe, tell all of your friends about it, share, and I'll see you next time. Bye-bye.